Hello, this is Ricky from Data Mastery. Welcome to our channel. In today's video, we are going to talk about something very important and something very interesting. This is about how you can stop wasting the LLM tokens, whether you have set up, the AI workflow in your organization, or you are just learning, or you have something like a POC kind of setup. The problem that many people face nowadays is the token limits, like how much limit is enough. If you're working in a bigger organization or larger organizations where you have, like, let's say you have set up the RAG workflows and you have tons of data, and then you are just bleeding tokens literally. You can increase the token limits and probably tweak some rate limits and whatnot, but this really does not solve the purpose of setting up some intelligent solution that won't actually so you won't have to actually use tokens for repetitive queries. Because let's say if you have set of documents, more or less the queries are gonna be similar after a while. So you probably have 100 queries. This is kind of a unique in the in the context of the meaning of the queries, like not the wording of the query, but the semantic search or the real context of the queries. So you can probably have 100 unique context or something like that. Now this is where things become interesting, because how you can make sure that you can leverage the existing response from the LLMs without any performance issues or without any issues or the drop in the accuracy. So today we're going to talk about the semantic search caching. Now this is one of the mechanism or the caching mechanism that you can use with your LLM or basically the RAG based workflows. There is also a concept called embedding caching, which means you can basically cache the entire embedding, so you don't have to generate the embeddings again for a similar type of documents. So in today's video, I'm gonna give a demo on how this concept actually looks like, because it looks fantastic in theory, but how is it gonna look like in practical or in the real scenario, and then how you can see, like whether this solution is really helping you to save some tokens or not. So this is kind of what you see on your screen is a rough workflow, which basically demonstrates two things. So let's start from the top. Let's say there's a new user query, and what's going to happen is when a user is going to enter the query, it is going to generate a hash from the query and the context. So I have set up a Redis cluster, like it's a local Docker container. So what I'm going to do is I'm going to create a hash key for the query, and the hash key consists of two components. One is the query itself and the other is the context. So I'm going to show you exactly how that looks like. Now, the next step is when the hash key is generated dynamically, it's going to look in the cache. It's going to look in the Redis cache whether there is an exact key that's already stored in cache. If it's yes, then that's the exact match, and the results are going to return from the cache. Now that is the simplest way of caching. What it means that you have documents. Let's say you have documents about AI, right? And you ask a question, what is AI? And you get a response, and that basically becomes what is AI plus the context. Now the context is gonna be the top n number of documents for this query. So let's say you have 10 documents in your data source. Out of those 10 documents, 5 are related to AI, but in your solution you are picking the top most, which is called top K, whether it's 2 or 3 or 5, whatever it is. So let's say we pick top 2. So that is the context. So the documents related to that query or the corresponding to that query, that is the context. So the query itself and those two documents, that will combine and make a key. Now, next time, if you ask the same questions or anybody else asks the same questions, what is AI? Then that's going to be exact match, because when you create the MD5 hash with the same query or same question and those two documents, the hash is going to be same. So if that key or that hash key is found in the cache, then that's the exact match, and you will get the data or the result from the cache without hitting the backend LLM. Now that is a very, very simple example. Now let's say if I change the query wording to, instead of saying what is AI, I'll say explain AI to me, right? Now the words are different. The query, if you take word by word, that is different now, but if you look at the context, that is same. Like, the meaning of this query, what I'm trying to ask, that is same. But in this case, in the simplest caching mechanism, it is going to create a new key because your query wording has been changed. Now that is not something that we want, because that is very, very rigid. I will get the result from cache only and only if the query is word-to-word match. Now this can happen, but the probability is very less. Now the second solution is, or the second approach is, to do the semantic search and basically understand the context of the query itself, right? So if I ask what is AI or explain AI to me, the meaning is similar. So I should get the result from the cache instead of hitting the backend LLM models. Now, how that looks like, let's say if there's not an exact match in the cache because the key is different, so what's going to happen is going to convert the query to the embeddings now. So you have embeddings already created out of your documents, and now you have a query and you create the embeddings of your query, and then you fetch all the stored query metadata. Now in this case, in the Redis cache, I am storing the key and I'm also storing the query itself. Okay, so what's going to happen is for the new query, I'm going to create the embeddings for the new query, and I'm also going to fetch the metadata. Metadata is actually the hash key plus the query which is already stored. And then I'm going to calculate the similarity between my new query and the query which is already stored in the cache. Now that is called cosine similarity. And you can set up some threshold value. If the value is 1, it means perfect match. So you can set up the value like 0.8 or 0.75, whatever makes sense. But don't set it too low, then the similarity is probably not going to match. So then if the new query is similar to the query I have stored in the cache. Now, the important point to note here is it doesn't have to match exact word by word. But what we need to match is the semantic match, not the exact match. And with this cosine similarity, we can do that. And let's say if the similarity is greater than 0.85, what it means, the results are going to return from the cache because it's a semantic similarity or a semantic match. If no, then you can call the LLM API and you create a new hash key, and you also store the query metadata with the embeddings. So this is the overall design of this demo basically. So you have two approaches. One is exact match, and like you see in the example, let's say what is LangChain, it's going to create a new hash key, and if there's an exact match, then the results are going to return from the cache. But let's say the query 2 is explain LangChain to me. Now what is LangChain and explain LangChain to me? Semantically, they both are similar, but if you look at word by word, they are different. So in this case, it's going to be a semantic match, not the exact match. And if you say what is token efficiency or any other totally different query, then obviously there's going to be no match. And then you will hit the LLM API and create a new key with this query and store the query metadata as well. And as I said earlier, I'm using Redis cache for this example. So I hope you understand the overall flow, and let me now open my IDE and we're gonna just run this code and I'm just gonna explain. So I have my Docker container running, which is just Redis latest image, nothing fancy. So the first thing that we're gonna do is install all these required packages. Since I have already installed this, so you can see that the requirements are already satisfied. And by the way, I'm using my virtual environment, so everything I install gets installed to the virtual environment. And I'm using my OpenAI API key for this demo. I have the API key in the .env file, and what I'm going to do is I'm going to load that OpenAPI key from the env file. And then I'm going to import some of these LangChain and other libraries. In this case, I'm going to use FAS as my vector store database. So here, I'm going to initialize my Redis client, basically connect to localhost with 6379 default port and flush all the cache, whatever existing cache is there, just flush everything. And then for the docs, I have these 5 kind of docs. I'm just like assuming, although these are like the 5 lines, but let's consider these are 5 docs. And that's what I'm gonna pass, and we're gonna create the embeddings for these docs. You can see I have a doc for LangChain. I have a doc for what LangChain offers. I have doc for OpenAI. I have a doc for token efficiency. I have a doc for vector store prompt templates. So assume these are 5 different types of docs. And you can see the Redis cache has been cleared, and I have loaded 5 sample documents. And the next thing is create the embeddings. So I have this OpenAI embedding module called here, or the library, and then I'm going to use FAS to store these embeddings. So this is my vector store database, in-memory database. So the vector store has been created successfully. Now in your case, if you have something already set up, then you probably use like OpenSearch or something else as your vector store database. Now this is the first example, or you can say the first approach, which is very basic, and that is based on the exact match. So this is a semantic cache class, and what it has 3 different functions. Get the cache key from Redis, and get from cache, it's basically get a response from the cache, and then add to cache. Let's say the query doesn't exist in the cache, like the key does not exist. If it doesn't exist, then add that new key to the cache. So these are 3 functions that it performs. And then you can just initialize your semantic cache class. And here what I'm doing is I'm going to use GPT 3.5 model to answer or to get a response based on my 5 documents. So out of my database, which is my vector store database, I'm going to get the relevant documents based on the query, and I'm going to get the two topmost documents. And then I'm going to concatenate those documents or the content of those documents and generate the context. Now, remember I said earlier, your hash key consists of 2 parts. One is the query itself, and the other is the context. So this is the context that we are generating. Now, this is the keyword, or you can say the flag that we have set up. If the cache is enabled, then get the data, or try to get the data from the cache. You can enable or disable the cache as well. It's just you can say a flip or a true false button or a parameter. And if no cache is hit, so this is a LangChain provides this functionality to get OpenAI callback. Basically, it's gonna invoke my OpenAI model, which is GPT 3.5, and it's gonna generate the response. So if it's not gonna get the result out of cache, it's gonna generate the response, and you will basically, it will also add to the cache. Now we have this class with three functions, and we initialize the class, and then we are trying to get the answer from my model. And here I have two options: either get the answer from the cache if it exists. If not, then get the answer from the LLM and also generate the new key and store to the cache, so that next time I run a similar query, I'll get the response from the cache. Now let's test it out. So the first query is, what is LangChain? And I'm going to pass this query to my function, which is answer with rag. And we will get the answer, and we will also get the tokens, the number of tokens basically used to generate the response for this query. And now you can see that we did not have anything in the cache. It's a brand new cache. So obviously, and this is the first query, so it missed the cache, which is quite obvious. And what I did, it actually generated the response. We got the response, and it also added this key to the cache. Now this key consists of the query and the context. Remember this, this is very important. And you can see we have 67 tokens used to generate this response, right? And the next time, let's say this is a second call, and the query is going to be the same query. What is LangChain? Now we already have a key that exists in the Redis cache for this particular query, and this is a word-by-word match. Let's run this. And you can see we got a cache hit. Why? Because it's an exact match. So if anybody is going to ask the same query, we already have this key generated in the cache, and we get the result from the cache now. And it's not going to hit the LLM. This is very, very important to understand. And you can see here, we have 0 tokens that we used. Like, this is how you can save the tokens, not by increasing the limits. Whatever workflow that you set up is going to catch up with the limit. But you have to have these mechanisms in place in order to preserve those tokens without any trade-off with the accuracy of the response of the model. You can see here, what is LangChain? LangChain is a framework for developing applications powered by language models. So it's a perfect response. There is no issue with the response. But we are not using any token this time. Now let's see the third time. As I said earlier, you can enable or disable the cache. So in this time, what we're going to do is we're going to call our answer with rag function, but this time I'm going to disable the cache. So what's going to happen? It's going to use the same amount of tokens again, 67. Now, this is similar to a scenario where you don't have a cache and you have users basically asking similar queries. And what you are doing, you are generating the response, but for each query, you are burning the token unnecessarily. If we have cache in place, you can return the response for similar queries without consuming an additional token. So this is the you can say the idea behind this approach that I wanted to share with you guys, and this is very, very, very important concept. Now the fourth test is a totally different query. What is token efficiency? Now guess what's going to happen? It's going to create a new key because nobody asked this query before, so we do not have any such key corresponding to this query in the Redis cache. So if you run this cell, you see that cache missed, which is perfectly fine. This is what we expected. And you can see here a new key has been added. And you also get response for your query, and you can see that you have 119 tokens used to generate the response for this. Now, how many keys that we have? So we have 4 keys in our cache right now. And you can also do some performance analysis, like we had token, which is token number 1, 3, and 4. These were without the cache, and tokens 1, 2, and 4 with the cache. Basically, token number 1 was that is something which we used to, which was the first query. So that's basically we are calculating in the both the scenarios, because you got to start from somewhere. So that was our first query. So that's why we have this thing, this token in both of our with and without cache result. And then we have token 2 and 4 with cache, and 3 or 4 without the cache. Token 4 is with the cache, but it generated a new key because there was no such key exist in the cache. So it had to hit the backend LLM API, generate the response, but the token 4 was actually using the cache. And if you do a simple math here, you have like tokens without caching 134 and tokens with caching 67. So you have this much percentage that you saved. But overall, the concept is hitting the cache for the similar query. Now, this was the first approach. In this approach, we have only seen the exact match cache, right? Now, what I want to do is, let's go back to the query, and what I want to do is, if I ask what is LangChain or explain LangChain to me, I should hit the cache, because the context or the meaning of both of these queries is same, right? The words are different, but not the context. Now, this is where you can extend this solution, and what we're gonna do now is we're gonna create a new class, and we're gonna extend our existing semantic cache class. And what I'm gonna do now is I'm gonna add to cache. This is similar to what we have seen earlier. Add to cache, get from cache exact, and get from cache, which is semantic search. And yeah, this is one, get from cache semantic. So basically what's going to happen now is the key difference is we are going to have the embeddings of the query for the semantic search, and we're going to have the meta key. Now, what is the meta key? The meta key is basically the query and the query embedding. That's what we save as the metadata. So when you create a key, this time it's going to have this key, which is similar to the exact match key that consists of the query plus context, but it's also going to have the query itself that will be stored in the Redis cache. Now, this is the same one. Like if you get the similar query, then you can just get it from the cache. And this is the model that I'm inheriting from my base class, which is semantic cache. And then the get from the cache function, what it does, it is trying to get a response from cache using exact or semantic matching. So this is going to decide whether it's an exact match or a semantic match. If it's an exact match, then call this function. If it's a semantic match, then call this function and pass query as input. For the exact match, you have to pass query and context as the input. So this is a definition of get from the cache, the semantic cache. So basically, here we are going to decide or calculate the similarity. This is a cosine similarity. So if your query is similar to the query which is stored in the Redis cache, then there is a similarity. So the similarity threshold can be 0.85, 0.8. So you can define that. And basically, this is where the similarity is calculated. And it's going to return the cosine similarity as well. Now, the next thing that you're going to do is create a class, and basically you can reset or record hit, record miss, or get the hit rate. And let's test it out. So I'm going to clear the cache, and then I'm going to initialize my class, which is enhanced semantic cache class this time. And I'm passing the Redis client and embeddings, time to live, and similarity threshold is 0.85. So this is where I'm defining the similarity threshold. And now I'm gonna get or try to get the answer from my LLM. Now in this case, we are again going to get the top two documents, top two relevant documents. We are generating the context here. If you're using the cache, then try to get the result from the cache. And you see here, we are trying to get from cache. And this method is what is gonna decide whether it's gonna use the exact match or the semantic match. And if nothing works, then call the LLM API and generate the response. So this is very much similar to what we have already seen earlier. Okay, now let's do another round of test. So we have empty cache. We cleared everything. So the first query is, what is LangChain? So this is gonna miss the cache, obviously. So you see here, the first query is, what is LangChain? And it's gonna miss the cache, which is dead. Now you see two caches here. So the one is the exact match cache, the other is the semantic cache. So both of these caches are missed, which is obvious because this is our first query and there is no such key or anything in the cache. And we got the response here. This time we have used 80 tokens. Now the second exact same query. So what is LangChain? We are passing exact same query. It's gonna hit the cache. So it has hit both, like, the exact match and the semantic match. Basically we got this from the exact match function because this is the exact same query. And you can see that we have 0 tokens used this time. Now this is where this new functionality will show how this is different than the previous approach. Now I'm asking, explain LangChain to me. Now if you look at word by word, this is a different query, right? And the hash key is also going to be different, but the context of this query is similar. So I should hit the cache this time. So let's see. And you see here, it has missed the direct cache or the exact cache, and that was expected, but it has hit the semantic cache, and that's what we wanted to see. So it has hit the semantic cache, and the tokens used this time is again 0. Now this is super powerful. Doesn't matter how you ask the query, if the context is similar, which is already stored in the Redis or whatever caching mechanism, then the query is gonna get the result from the cache, and you will not be spending any money on the tokens. This is super powerful and super important to understand. And then I have another query. What is token efficiency? A brand new query, as expected, it's going to miss the cache. And we get like a response and 92 tokens used. Now, another semantically similar query. Tell me about the LangChain framework. So this is similar to what is LangChain, or explain LangChain to me, or tell me about the LangChain framework. Words are different, but semantically, they all are similar. So let's run this. And you can see again, it has hit the semantic cache, 0 tokens used. Now you can just run this function. This function basically what it does is it's going to list out the keys from the cache. So this is the difference. Pay attention to this one. Now we have two set of keys here. We have result cache keys, and these keys provides exact match, right? If it's exact match based on this key, then we get the result from the cache. And the other type of keys that we have is the metadata. So what is metadata? We have query meta, which contains your key, and it also contains your query. So when the cache contains what is LangChain, and you're asking explain LangChain to me, now this is where the cosine similarity is calculated between your query and between the data that's in the cache. Now if the data in the cache has similarity greater than 0.85, then you get the result from the cache. Otherwise, you hit the LLM API. So this is where this enhanced approach, this is how it works. So you're not storing only the key, you're also storing the query. Now, when you ask the new query, we all know that it gets converted to the embeddings. So you have the embeddings of your new query, and you also have the embeddings of what's stored in the cache. And if there's a similarity that meets or exceeds your threshold, then you will get the result from the cache. And then you can just do some calculations and see, like, without semantic caching 332 tokens, with semantic caching 172 tokens, you have saved 160 tokens, and you have saved almost 50% of the tokens. So I hope it really helped you to understand this concept. Now, as far as this coding is concerned, I used Cursor to do all of this coding. So I do vibe coding. No way I spent like so much time writing this notebook or writing this code. I just want to explain this concept, and this is super, super important to understand these kind of, you can say, concepts or approaches that you can implement in your workflow. And I hope that when you next time try to implement RAG workflow, or you revisit your existing implementations, or if you hit any token limits, or you're spending too much money on the tokens, I hope you remember that there is a way to preserve some of these tokens and stop the wastage. And I hope that you go ahead and implement the caching mechanism. Now, there's another mechanism which I explained earlier in the beginning of this video, which is caching of the embeddings itself. This demo was more of a semantic search caching. That caching mechanism is embedding caching, where you basically generate the embeddings and you cache that, so that you do the search against the embedding stored in your cache rather than hitting the LLM API every time. So I'm going to make a video on that as well. In one of the upcoming videos, I'll cover that topic. But yeah, let me know if you guys want to have any other interesting topic like this that you want me to cover. I'll definitely make a video on this. So my idea is to get these interesting topics to you, because this actually got this idea I got from another issue that I was trying to solve. So I got this idea. I'm like, okay, let me create a video on this so that I can share it with all of you, so that you can get some benefits out of this. So I hope this video is helpful. If you like this video, do subscribe to our channel. And any questions, just ask in the comment sections. We'll be happy to answer. And if you, as I said earlier, if you want me to make any video on any similar interesting topics, do let us know that as well. So your feedback is highly valuable, appreciated. So thanks again for watching, and stay tuned for more interesting videos. Cheers.